Hello, this is the first video in a series of several videos where you will be suffering through the rest of Mr. Johnson's lectures. The lecture for today, or at night, if you're doing this at night, is piston engine ignition systems. Yay! First of all, you need to understand a few things about the basic operation of a reciprocating engine, or piston engine if you prefer, so that you can understand why the ignition system is doing what it's doing. A piston engine has 4 strokes. In that, inside of the cylinder, the piston, first stroke, it goes down, and air and fuel mixture comes in. That's the intake stroke. Then the piston goes up, and it compresses the air fuel mixture. That's the compression stroke. The next one is where the spark plug fires and the fuel air mixture catches on fire. It gets hot. It tries to expand, but there's limited volume, so the pressure increases on top of the piston, pushes the piston down. That's called a power stroke. Then the last part is where the piston goes up and expels the burned up fuel and air. Now you need to understand that you'll notice that the piston goes down, goes up, goes down, goes up. The crankshaft that the propeller is bolted to has to rotate around twice. The crankshaft has to rotate around twice for the piston to go down, go up, go down, and go up. So to go down and go up, the crankshaft rotates around once. That would be 360 degrees of rotation. And then the piston has to go down and come back up again. So there we'd have another 360 degrees of rotation. Essentially what that means is we could also look at these events occurring based on where the crankshaft is in how much it's rotating in degrees. So one way to do that is like this. The first 180 degrees is the intake stroke. Then the next 180 degrees is the compression stroke. Then the next 180 degrees is the power stroke, and the last 180 degrees is the exhaust stroke. Now normally, if you think of this without taking into account too many details, this power stroke, that's the one where the fuel and air mixture is catching on fire and the pressure is going up and pushing the piston down. Now, the problem with this only having 180 degrees of power stroke is that this is a limited time. If the engine is running at 500 RPM, this is a lot of time. But what if the engine is spinning at, say, 2500 RPM? Then this isn't a lot of time. So what's going to happen is we're going to need to turn on or start the power stroke, or at least we're going to have to start the fuel catching on fire before this point right here. This point right here would be where the piston is all the way up at the top and then starts coming down. This is called top dead center, when the piston is all the way up at the top. What airplane magnetos are going to do is 20 degrees of crankshaft rotation before top dead center is where the spark plug is going to fire. So the spark plug is actually going to fire so the fuel can start burning 20 degrees of crankshaft rotation before the piston gets all the way to the top. Now the nice thing is this piston is only about 1/8 of an inch from the top, and as the fuel starts to burn just before the piston gets to the top, the pressure hasn't had a chance to rise too much. So at high RPMs, this is a very, very short period of time, but that little bit of extra time is worth it. This 20 degrees before top dead center is a very common time or position of the crankshaft and position of the piston on airplane piston engines when the spark is going to fire. Now, automobiles, they have variable ignition timing. That is, the spark plug fires at a variable time. That is, the spark plug can change what time. The spark plug doesn't change it, but the ignition system can change when the spark plug fires. In piston-powered airplane engines, except for a few exceptions, which we'll get to at the end, the spark plug fires always at this 20 degrees before top dead center. Some airplanes it might be 22, it might be 24, it might be 18. But when the magneto is bolted to the back of the engine, this 20 degrees before top dead center is set, and then it doesn't change. You'll notice that when you pull an airplane engine to idle, say a 172 to idle, it tends to run a little rough, kind of blub, 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 blub. It's because the spark is firing a little sooner than it should, because it's firing at 20 degrees before top dead center. The piston is coming up and the spark fires. It does have a little tendency to push the piston back down, but the inertia of the engine gets it past that last 20 degrees. You'll notice in a 172 or a Seminole that if you push the throttle up past about 1,000 or 1,200, the engine smooths out quite a bit. It's because the 20 degrees before top dead center works a whole lot better at the higher RPMs. So the purpose of the ignition system is so that we can have an ignition or a spark inside of each aircraft cylinder at the appropriate time. And when is the right time to fire? We're going to say for test purposes that the right time to fire is 20 degrees of crankshaft rotation before top dead center, BTDC, before top dead center. That's 20 degrees of crankshaft rotation before the piston quite gets all the way to the top. Now, what happens after the spark plug fires? If we look at the top of a cylinder, and here's a spark plug, and here's a spark plug, and we were looking inside of the cylinder from the top, and we were looking down at the top of the piston, we would see at 20 degrees before top dead center, the spark would fire, both spark plugs will fire at the same time, and we'll see this flame propagate across the top of the piston. The speed of this propagation, which you do not have to know for the test, is about 100 feet per second. It's not really that fast, it's only about 1/10 of the speed of sound, but when you only have to cover an inch or two, that's not too bad. If this engine was detonating, instead of this being 100 feet per second, it would be supersonic. Detonation is when essentially all of the fuel catches on fire at the same time. And detonation is bad. For instance, let's say that the piston is pretty much almost all the way up to the top, and we catch all of this on fire at once. At the same time, we're going to have an extremely high pressure pushing on the piston and pushing against the cylinder. If we detonate the engine for too long, since it's causing more stress to the cylinder than it's designed for, that metal cylinder might come flying off, and that's typically not a good thing in flight. So what happens in the engine when the ignition fires, we have a smooth but rapid propagation of the flame front across the top of the cylinder. Now this takes some time. That's again why we need to fire the spark plug a little bit before the piston gets all the way up to the top. So after the spark plug fires, we have a smooth but rapid fuel burn, and the flame propagates across the top of the piston. Diesel engines found on trucks and on a few kinds of cars, we are going to say for test purposes, do not have an ignition system. Now it's true that on most diesel engines there's a glow plug. A glow plug is essentially just like a cigarette lighter. You run electricity through a coil of wire, the coil of wire gets hot, and when it's cold or on cold days, a diesel engine, it's a little harder to get started, but so they use a glow plug. But once the engine gets running, they don't use the glow plug. So we're going to say that diesel engines don't have an ignition system. Diesel engines work by this piston coming up so stinking high to the top of the cylinder that we get about a 20-to-1 or a 25-to-1 compression ratio. That is the volume of when the piston was all the way to the bottom compared to the volume of the piston when it's all the way to the top, has a ratio of 25-to-1. And so the air gets compressed. The air gets compressed so much that it gets hot. The air in a diesel engine, that fuel-air mixture, gets so hot that it catches on fire without an ignition system, without a spark plug. You could even say that a diesel engine detonates all the time. If you ever drive behind a big giant pickup truck with a diesel engine in it, and they're tromping on it, you see all that nice black smoke, and you can hear it detonating. You can hear it pinging like crazy. That's exactly what it is. But on those engines, the metal around the cylinder is a whole lot thicker than it is on an airplane engine, because airplane engines, we want them to be nice and lightweight. So diesel engines can withstand the detonation. Battery ignition system is what you find on most cars and motorcycles. It's called a battery ignition system because it runs off of the electrical system of the vehicle, which during start is only powered by the battery. When you're cranking up your car, the alternator isn't working until the engine is rotating. So the only place you can get electrical power for the starter and get electrical power for the ignition system is from the battery. On automobiles, if the battery is completely dead, or removed from the car, you can't push start it because there's no electrical power coming out of the alternator. So there's no electrical power to the bus bar, so there's no electrical power to the ignition system. Cars and motorcycles have battery ignition systems. If the electrical system of the car is dead, then the ignition system of the car will not operate. There's two types of magneto systems found on airplanes, the low tension system and the high tension system. In both cases, there is a step-up transformer to kick the voltage up to a really, really high voltage. But in the low tension system, there is a separate step-up transformer for each individual spark plug. And in fact, they'll have to bolt this, it's a little smaller than the size of a fist. They'll bolt this step-up transformer on the end of each cylinder. This is a very rare ignition system, even for airplanes. In fact, if you went out to the airport right now, probably the only place you'd find it, I think there's an old King Air, an old Beechcraft Queen Air out there, and it might have a low tension ignition system on it. But 99.9% of the time, small piston powered airplanes have a high tension ignition system. And so that's what we're going to concentrate on for the rest of this lecture, is high tension magneto systems, or high tension ignition systems. You could say that there's three basic components that you can see that comprise or make up an ignition system on a piston-powered airplane engine. The magneto, the spark plug cable or the ignition cables, and the spark plugs themselves. The magneto has a permanent magnet inside of it. It has a permanent magnet inside of it. It is an extremely strong permanent magnet. It produces 100% of the field, of the magnetic field, unlike a regular generator or an alternator, let's just say, unlike a regular generator that has a permanent magnet, but it also has a field that the voltage regulator allows current to flow through, so you have an electromagnet as well, but not so in a magneto. We only have a permanent magnet. But it is an amazingly strong magnet. If you took the magnet out of a magneto and stuck an electronic watch next to it and touched the magnet with your watch for a second or two and pulled the watch away, you probably would have ruined your watch. It is that strong of a magnet. It provides all of the electromagnetic induction because it's getting rotated by the engine. Of course, we already know that the characteristic of a generator is that it has a permanent magnet and it is self-exciting. Those are the two characteristics of generators. But with a magneto, there is no electromagnet, there's no field winding. All of the lines of flux come from the magnet because it is so strong. In a car or a motorcycle, if the electrical system on the vehicle goes dead, the ignition also goes dead. But on airplanes, the magneto is completely separate from the electrical system of the airplane. You can be flying along at cruise altitude in a 172 or a Seminole and turn off the electrical master switch, turn off the alternators, and have absolutely no electrical power in the aircraft electrical system, but the engines won't notice because the magnetos are producing 100% of the power that it takes to run the ignition system. There's two of them. It's redundant. I think that leads us into the next question. Yeah. There's two reasons why aircraft have two ignition systems. Well, the first one is redundancy or safety. The FAA requires that there be two ignition systems on FAA certificated piston engines, so if one fails, one ignition system fails, the other ignition system will still run the engine. Now, granted, it won't run it as well, but you ought to be able to maintain most of your power. The other reason why there's two ignition systems is that it is designed that way. If you look at this flame propagation, if we got rid of one of the spark plugs, it would take longer for the flame to propagate across the cylinder. In fact, that's what happens when you're doing an engine run-up and you turn one of the magnetos off. You'll notice the engine doesn't run as well. It's because the engineers, knowing that they have to have two ignition systems, go ahead and design the engine to run its best when both are operating. So the second reason why there's two ignition systems is that it's designed that way. Okay, the basic operating cycle of a magneto. I recommend that you get out your diagram and take notes on it. Basic operating principles of a magneto. First of all, there are three items inside of the magneto that rotate. They're all hooked together with gears, so they all rotate together in synchronization. That's the permanent magnet, that's the camshaft, and the rotor. We also have here, we have the ignition switch, which is also sometimes called the magneto switch. Got a wire right here called the P lead. There is a capacitor inside of the magneto, but we're not going to be discussing it in this class. We also have the breaker points. This coil right here is the primary coil. We also have the secondary coil. And each one of these is a spark plug. There is, that's true, a highly permeable core between the primary coil and the secondary coil, and certainly it concentrates the lines of flux, but we're not going to be discussing it. Okay, those three items that spin with the engine. The magneto is always bolted into the engine. You cannot disconnect it. The permanent magnet rotates. The rotor inside of the distributor rotates. And the camshaft rotates all the time. Now, the lines of flux coming off of the magnet, and I'm going to oversimplify them here. Lines of flux coming off of the magnet cross the primary coil. They're certainly going to induce a voltage, and if there's a complete circuit, they will also induce a current flow. The vast majority of the time, the breaker points are closed, and so our complete circuit is through the breaker points. You'll notice this ignition switch here is drawn in the normal, is in the on position. In the on position, that switch is open. So if we have lines of flux crossing the primary coil, it's going to induce a current flow. If we have a current flow because there is a closed circuit or a complete circuit, then we're going to get lines of flux being produced because of the current flow inside of the primary coil. Now this is a schematic diagram of the secondary and primary coil, but in reality they're wrapped around each other with that permeable core. So if there are lines of flux being produced by one, when these lines of flux collapse, they will collapse across the other coil. Now, the faster these lines of flux collapse, the faster they travel across the secondary coil, the greater the voltage is going to be induced into it. So we need these lines of flux to collapse as rapidly as possible. What's going to happen is just as this magnet is crossing and we get the greatest lines of flux, or cause the greatest current flow, so we get the greatest amount of lines of flux in the primary, the camshaft is also rotating and it's going to open up the points. At the same time, the rotor is going to rotate and it's going to point towards a different spark plug. When these points open, we no longer have our complete circuit for current to flow, so the current flow will stop. If the current flow stops, these lines of flux will collapse. As they collapse, they will collapse across the secondary coil, inducing a voltage, and if there's a complete circuit, it'll have a current flow. Well, the voltage has to be high enough to jump the little gap at the spark plug, and typically 20,000 volts is about what an aircraft ignition system produces. And you also need to know that the primary coil and the secondary coil are essentially a step-up transformer. There's only a few coils of wire in the primary, but there are many, many coils of wire or windings inside of the secondary coil. So when these lines of flux collapse due to one coil, they're collapsing across many, many lines of many windings, and so the voltage is much, much higher. If this voltage is high enough that it can jump the gap, that is, it can overcome the resistance in the cylinder at the spark plug, then we'll get some current flow across that air gap. It's essentially like a very small lightning bolt, and of course it'll be hot enough that if there's a stoichiometric ratio of fuel to air, then we'll get the fuel-air mixture to catch on fire. And just so you know, in case you're curious, the complete circuit for the spark to flow is through the primary secondary coil. Now what you need to understand is, what's I think one of the difficult things for people to understand about magnetos, is that the magneto switch is open in the on position. When you turn a magneto off, you're actually grounding the magneto. For these lines of flux to collapse rapidly, that's when the points have to open. But if this is closed, and that's now in the off position, when these points open, we'll still have a path for current to flow through the on-off switch, and the lines of flux will expand and collapse very slowly. If they expand and collapse very slowly across the secondary coil, the voltage will not be high enough to jump the spark plug gap. So although the magneto may be spinning and producing lines of flux expanding and collapsing, they won't collapse fast enough unless the points do the opening, because the switch is in the open position and it won't provide a path for current flow. So when you turn the ignition switch to the off position, you're actually grounding the magnetos. To turn it off so that there is a path for current flow and the lines of flux cannot collapse rapidly. Okay, let's do a review. You should be looking at your schematic, and we'll see how well I did here. The magnet, the cam, and the rotor all spin. They're all geared together. They're all geared into the engine. They're all moving around synchronized together. The flux from the magnet is moving, and since it crosses, those lines of flux cross the primary coil, that's electromagnetic induction. We induce a voltage, and since the points, the breaker points, are normally closed, that is an example of a spring-loaded, normally closed switch, Going through the breaker points, we have a complete circuit, so in addition to inducing a voltage, we're also going to have a current flow. Since we have current flow going through the primary coil, when we have electrons going through a wire, we get a little heat, and of course we get electromagnetic lines we get lines of flux. So because of the coil having current flow going through it, we now have flux that is generated around the primary coil. The breaker points open. They come open right when the lines of flux are at their greatest size. They come open right when the rotor is pointing to the next spark plug that is supposed to fire. When those points open, the current flow going through the primary coil stops. If there's no current flow, then there's not going to be any lines of flux. But the lines of flux don't just disappear, they collapse. They collapse rapidly enough with the breaker points opening that they will induce a voltage across the secondary coil. If the voltage induced across the secondary coil is high enough, because there's enough lines of flux coming off of the primary, because they collapse fast enough, then we will induce a voltage across the secondary coil that is high enough to push or exceed or overcome the resistance in that little air gap at the spark plug, and we'll get a complete circuit by going through that air gap and through the primary coil, and we'll have a little lightning bolt at the spark plug, and it'll catch the fuel-air mixture on fire. Yay. Okay, extra components. Now, what you may recall from just a minute ago is that in order for us to have a high enough voltage induced across the secondary coil to jump this spark plug gap, is we have to have enough lines of flux and they have to collapse fast enough. Well, one of the bad things about a piston engine is during engine start, the engine doesn't rotate very fast. We'll say the engine rotates at 25 RPM during the starting sequence. That's not very fast. That means that the magnet inside of the magneto isn't rotating very fast. It doesn't create very much current flow through the primary. We don't have much lines of flux around the primary, so when they do collapse, they don't do very much to the secondary coil. So we need a method to be able to get a spark even though the magnet inside the magneto isn't spinning very fast. And there are two ways to do it. There are two different systems that are used during engine start on piston engine airplanes so that we can get a good spark during engine start. One of them is the impulse coupling. The impulse coupling is bolted on between the magneto and the engine. Here's a picture of a magneto, and inside the impulse coupling is bolt into the engine. Inside the impulse coupling is a spring, and there's a mechanism that has weights in it that move with centrifugal force. What occurs in an airplane engine with a magneto that has an impulse coupling is while the engine is rotating, instead of spinning the inside of the magneto with the magnet and the cam and the rotor, it winds the spring. This energy is saved up, and then when it's time for the spark plug to fire, the spring is released, and it spins the inside of the magneto really, really fast. Now, one thing that the impulse coupling does, in addition to spinning the magnet really fast, is that it retards the spark. Now, normally, in an airplane engine, the spark plug fires at 20 degrees before top dead center. What this magneto is going to do is it's going to delay the spark by about 25 degrees, so it fires 5 degrees after top dead center. Because when the engine is spinning really, really slow and the piston's coming up to the top, if we fire the spark at 20 degrees before top dead center, it might actually push the piston down because it's going so slow and there's not very much inertia in the engine. So the second thing we need to do during start, in addition to having the spark plug, or to having the spark fire even though the magnet's not spinning fast, is we also need to retard the spark. That is, have it fire later than normal. And we're going to say it delays it about, and these are all generic numbers, we're going to say it delays it until 5 degrees after top dead center. So the two things that an impulse coupling does is, one, it spins the magnet really fast, even though the engine is fast, so we can get a good hot spark. And two, it retards the spark, or it delays the spark from occurring until about 5 degrees after top dead center. Now the inside of the impulse coupling has weights in it. It is operated off of centrifugal force. The faster you spin it, at some point it doesn't work anymore, and the magneto operates as we have previously discussed. We're going to say that impulse couplings only work below 300 RPM. If impulse couplings work below 300 RPM, that means while you have the key engaged and you're cranking it from 0 to 50 or 25 or whatever you're cranking it during start, the impulse coupling is going to work. And so we'll get a nice hot spark, and it'll retard the spark. The engine will fire. But you'll notice, you probably noticed if you've operated a piston-powered airplane engine, that it doesn't idle below 300. On the contrary, it probably idles at 5, 6, 7, or 800 RPM. That means the impulse coupling is not operating at idle. At idle, as previously covered, the engine runs a little rough. It's because even at idle, the engine, the magneto rather, is still firing at 20 degrees before top dead center. The only time the impulse coupling works is during start, because it only works below 300 RPM. The other type of system is the vibrator and retarded spark type of system. I have a nice schematic. We'll take a look at that schematic. No, you're not going to have to draw this on the chart, but essentially when you hit the start switch with an airplane or helicopter that has a piston engine with the vibrator and retarded spark system, you're causing a lot of electrical connections, a lot of switches to occur. Essentially, you're going to be doing two things. First of all, since the engine is rotating really slow and the magnet isn't rotating fast enough to do any good, what's going to happen is when you have a vibrator and retarded point system, it's actually going to hook up the battery to the field, and there's going to be a relay between the battery and the field. When this relay closes and it lets current flow go through the primary coil, we get our lines of flux. When this relay opens, the circuit is opened, the lines of flux collapse, and we get a current flow. When these lines of flux collapse across the secondary, we get a high voltage and a current flow through the spark. It doesn't even matter what the magnet is doing. Now, this relay opens and closes about 10 times per second. Now, let's say that when this relay is closed, then every time the current flow goes through the circuit, it's going to cause this relay to open up because it knows that a spark is fired, and then it's going to close again. So these lines of flux are going to expand and collapse at about 10 times per second. In fact, if you stand next to an engine with a vibrator and retarded points starting system, you can actually hear this relay buzzing at about 10 times a second or so. That's why it's called the vibrator and retarded point system, is because you can hear this relay vibrating. This system is also called the shower of sparks ignition system, because instead of there just being one spark, there are several sparks in its place. So it actually starts at the engine easier, because instead of when the piston comes up and you have a fuel-air mixture, you get one spark, as with the impulse coupling, you get many sparks. In fact, if you could look inside the cylinder with this operating, you'd see what looked like a shower of sparks coming from the spark plug, hence the term shower of sparks ignition system. And I'm not going to get into it too much in detail, but this also has a second set of breaker points. and they are retarded about 25 degrees. When you rotate the start switch, it turns off this set of points and engages the retarded set of points. So guess what happens to when the spark plug fires? Yes, you're right. It retards the spark 25 degrees from what it was, and again, we get the sparks to fire at 5 degrees after top dead center instead of on top dead center. So the vibrator and retarded spark system, or the shower of sparks ignition system, does two things. It gives a really hot spark during start, even though the magnet is spinning really slow, and it does it by using aircraft battery power to go through the primary coil. And the second thing it does is it retards the spark, or causes the spark to be delayed, by using a second set of retarded points, so that those points open later than normal. Now, when does it operate? This doesn't use any centrifugal force on some weights inside of an impulse coupling. It only operates when the starting switch is engaged. It only operates when the starting switch is on. As soon as you let go of the starter switch, the magneto goes back to the way it was operating when we were looking at this schematic and looking at how it worked in the first place. Both of these systems, the impulse coupling system and the vibrator and retarded point system, only operate during the starting sequence. After the start is over, neither of them operate, and the magneto runs just like previously described. Of course, what's very interesting is with the impulse coupling, it's completely separate from the aircraft electrical system. So if the battery is dead and you have impulse couplings on your magnetos, you can go out and you can hand prop the engine. Just watch out for chopping your head off with the propeller. If you have an airplane or a helicopter with the shower of sparks / vibrator and retarded breaker point system, then it's dependent upon the aircraft battery, and if the battery was completely dead, you could try to hand prop the airplane, but it wouldn't do any good because the magnet inside of the magneto wouldn't be spinning fast enough. Also, on the airplanes with shower of sparks ignition system, since one of the magnetos is providing many, many sparks, when you turn that start switch to the on, it grounds out the other magneto so it doesn't fire too soon. And it also typically has a second set of points, but now they use that second set of breaker points with a wire connected to a tachometer, and it counts how many times per minute the breaker points open and close, and that it can be used for a tachometer in the cockpit to tell you how fast the engine is spinning. Also, air has a lot of resistance compared to a vacuum. A vacuum, electrons can jump across it much, much easier, or has less resistance than that of air. Inside of a magneto, you don't want electrons jumping around where they're not supposed to. So if you're going to fly an airplane, a piston-powered airplane that's pressurized, it's very likely that you're going to have pressurized magnetos. That is air from the turbochargers in addition to being pumped into the engine so the engine can have enough power at altitude, in addition to the turbocharger pumping air into the cockpit so the cockpit stays pressurized. You're also going to pump some of this turbocharged air, this pressurized air, into the magnetos. If you were climbing, let's say in a Cessna 340, for instance, and you were getting past 20,000 feet and one of your engines started to run rougher and rougher the higher and higher you climbed, if you started descending and it got better, it's possible that what could be causing that is one of your magnetos is leaking air and isn't staying pressurized, because then the electrons are jumping around inside of the magnetos instead of going where they're supposed to. Now, in the automobile industry, a couple of decades ago, they started in with electronic ignition systems. Well, they have finally started putting electronic ignition systems on airplanes, but they're very expensive and they're not very commonly used. However, the electronic ignition system does what that does in cars. During engine start, it retards the spark, so the spark fires later than normal, so it's easy to start. And when you're at idle, instead of being at 20 degrees before top dead center, it might be at 2 degrees before top dead center. The faster you spin the engine, the more you want to advance the spark towards 20 degrees before top dead center. Whether you're at cruise or full power or climb power or at idle, it's going to vary the ignition timing. That is, it will change when the spark plug fires from 20 degrees before top dead center all the way down to 5 degrees after top dead center, and it does it based on what the engine RPM is. Now, the two good things about electronic ignition systems are, one, the variable ignition timing improves fuel economy. You can burn less fuel and get the same amount of power, so your gallon per hour burn rate is lower. Number one, better fuel economy. Number two, you get more horsepower out of the engine than you would have otherwise. That 20 degrees before top dead center, since the engineers could only pick one time when the spark plug could fire, they had to compromise between when was the best time for the spark plug to fire for takeoff power versus when was the best time for the spark plug to fire for cruise power. So it's not perfect for either cruise power or for takeoff power. But now, since you can vary it, you can get more horsepower during takeoff, and you get better fuel economy during cruise. What a deal. The thing about electronic ignition systems is the FAA doesn't let it be certified unless there's a backup system. There's two ways that the backup system I've seen, there's two types of backup systems. One is they leave the original magnetos on the engine, and they only work when the electronic ignition system fails. So if the electronic ignition system craps out, the magnetos will kick in and you'll have your backup ignition system. The problem with the electronic ignition systems is that they run off of aircraft power. And what if you're flying a 172 and the alternator and the battery quits? You're going to be unhappy. So on the airplanes with the electronic ignition system that don't have backup batteries, they install a backup generator on the engine. And the only thing that this little tiny generator does, it's about the size of a fist, the only thing this generator does is provide electrical power to the electronic ignition system. So if you have an aircraft electrical system failure, this generator will provide enough electrical power on its own, completely separate from the aircraft electrical system. It'll provide enough power to run the electronic ignition all by itself. If you decide that you're going to hand prop an airplane engine, you need to be careful. It is extremely dangerous. It is easy to chop off your head. It is easy to chop off your leg. It's easy to chop off your fingers or arms. If you're going to hand prop an airplane, tie the tail down and pull the airplane tight against the chain, and then put chocks on the main wheels. After you get the engine running, then you can untie the airplane with the chain. Then you can pull the chocks out. But don't trust your life to somebody inside of the airplane holding the brakes. Yes, they should hold the brakes as well. You also don't want anybody operating the airplane engine from inside the cockpit that doesn't know how to operate an airplane engine. For instance, Massey Ferguson tractors, when you push the throttle forward, that slows the engine down. When you pull it back, that speeds it up. So someone who's used to operating a tractor would screw it up, and when you try to slow the engine down, they'd end up speeding it up. Also, I highly encourage you to brief what words you're going to say that mean the ignition is on and the ignition is off. You notice the sound aw is in the word on and in the word off. So I highly encourage you to use the words off and the word contact. Contact meaning the ignition is hot. I've only hand propped an airplane twice in my life, and half of those times that I've done it, I've almost died because the ignition was on when I thought it was off. And I pulled the propeller through, and the engine started when the spinner was about 6 inches away from my nose. The only thing that saved me was that the pilot was holding the brakes. Of course, if you have to hand prop it because the battery is dead, I would say that the battery is unairworthy unless you knew why the battery was dead. If you're going to go fly an IFR on one alternator, that's what I call single alternator IFR, I would recommend that you not go because you don't really know if that battery is going to be able to hold a charge and get the entire amp hour rating out of it in case the alternator dies. If you have any questions on piston engine systems, you should come and see me in my office, send me an email, call me at home about 4 o'clock in the morning. I'm sure I would appreciate it. That is all for piston engine